We'll get started in just a minute. I'm just trying to figure out a couple things I've been trying to do. So hold on. I'm sure you guys all be fine waiting for a minute. We're in no hurry. Let's see here. Well, darn. Okay, so the reason I was taking it here is I'm trying to open another Zoom window so that I could see everyone instead of just seeing like the top 6 people up here. As you guys are probably aware, I need to keep my video pinned so that if you look at the recording of the video later, I don't look super tiny and you can't read the stuff on the board. So unfortunately, I wasn't able to do that, so I can only see the top like 5 of you, and I have to scroll through if I want to see other people. So again, really appreciate seeing your live faces, but again, if you don't want to be on video, totally understand. I don't want to be on video today. My hair is not looking excellent, but whatever. That's the COVID hair. But if not video, a picture is also great, just so I can kind of identify faces with names. That'd be excellent. Let's see here. So also, I do want to encourage everyone to speak on microphone. You're welcome to type things in the chat, but I would love to hear voices as well. So if you have questions, also I should turn my volume here. If you have questions, don't hesitate to actually ask them with your voice because it's good to hear real people. Let me close a few things here. Want to let y'all know as well, I did post a number of videos to YouTube yesterday covering various things. In fact, if you want to go look at them for just 1 second here. So one quick moment. I'm going to share my screen for just a second here. I want to share my, okay, let me email up, but here, yeah. So sharing my screen, yes, great. So you want to take a look for a second, you can see there's a bunch of videos on Canvas, sorry, not on Canvas, on YouTube. And I did make them all public, so you don't have to like just link from Canvas anymore. You can just go to the YouTube, my YouTube webpage. And then if you, I know there's a way to sort these somehow. I feel like there's something here. There's a way, I know I've tagged all the ones for our class as being 16B. I don't know exactly how to see that now because I'm not great at this. Oh, I don't want to watch my video. Okay, anyway. So if we click on that little thing up there, then you can go down to this part here, show more. And there's where I can find, at least I can find, all the Math 16B videos I've made. So there's the beginning to the end, the intro, and then I made some videos on exponent rules, log rules, more log rules, and the derivative of the natural log of x. And I thought I had made another video as well. Maybe it didn't get posted. I had made a video on the derivative of, yeah, where did you go? Did I forget to post it? Oh, well, I have another video to post for you guys. I guess I'll have to do that after class. Yeah, I don't want to go there. Sorry. Oh, no, I forgot to tag it with 16B. So let me just, let me edit this real quick. Yeah, shut up. Sorry, I want to make sure this is easy for you to all find. So I can, yeah, I need to add it to the 16B playlist. There we go. Cool. So those are there for you guys if you want to watch them. I think they're fine. I mean, they're just like 5 to 10 minutes to kind of show some examples. Let me stop sharing my screen here. All right, great. So I guess, so before we get started here, someone did send me one question, which I thought was good. So I'll probably just start with that example. I changed it up a little bit just to make it slightly different, and then we will move on from there. So you should be thinking, if you have a question that you want answered or an example that is similar to an example that is on a homework problem, you can definitely do that. I've got a few ideas, and I've gotten stuff from Merck's and from FAM up and available to look at, so we can definitely do some examples. But let's go ahead and look at this problem that's very, very similar to the problem that someone just sent me yesterday. Let's see, let's make sure this is not terrible here. This thing really likes to tighten up on its own. Okay, so here's the problem, which is hopefully legible. I'm going to read it to you guys as well. Also, I need you guys to talk. I don't know if I said this to everybody else, but I need you to talk so that I talk less, because my voice is doing all right today, but definitely Tuesday I was like, ooh. So here's what we have. The sales, S, in millions, for a pizza chain from 1989 through 2004 can be modeled by the exponential function S of t equal to 150 times 1.1 to the t power, where t is measured in years, with t equal to 9 corresponding to 1989. Below this, I wrote, this is dumb, because this is a dumb, like, no one would ever say you're going to start at time equals 9 being this year. You would just say what year t equals 0 was. But this is to make you have to think about what year t equals 0 is. So really, any normal person or normal textbook would have said t equals 0 is 1980. Or whatever it happens to be, right? I just subtracted 9 from 1989 to get back to 0. Use the model to estimate the following things. So the question that I received was just to estimate the amount of sales in these years, or whatever years we're given. But we're also going to talk about the rate of change of sales, because that's where we're going with this eventually. So I'm going to write this on the other side of the board because I kind of have a lot of room here. But this is the idea. We've got this function, and we're trying to figure out what these are. So before we actually do that, we should say, okay, if we're looking at 2010, we should say what year that is. Well, t equals 0 is 1980. So 30 years later, that's going to be t equal to 30. And 40 years later, that's going to be t equal to 40. So that's what we're trying to figure out. What the sales are at time equals 30 and time equals 40, and what the rate of change of sales are at, again, time equals 30 and time equals 40. And hopefully I didn't pick numbers that were obscenely too large here. Let me just check something real quick. Where is that button I'm looking for? Yeah, let's see. Oh no, that's not going to be terrible. Hold on. Okay, good. So let's go to the other side. So here's again our function. S of t equal to, where'd you go here? Sorry, 150 times 1.1 to the t. And this is in millions, meaning just to kind of give you some perspective, the sales at time 0, which is 1980, that would be 150 times 1.1 to the 0th power, but anything to the 0th power is just 1, that's just 150. But it's not $150, it's $150 million because it's sales in millions. So in 1980, sales were $150 million. I just like the dollar sign, right? So that's how we're answering this question. All right, so we're trying to figure out what S of 30 is. Wow. Right, numbers correctly here. Right, so sales in 2010, so S of 30, we're just gonna plug in 30. That's gonna be 150 times 1.1 to the 30th power. And then I need to use a calculator for that because, well, right, I'm gonna do 1.1 to the 30th, and then I'm gonna multiply that by 150. Here's what I get. I get approximately 2,617.4. And the question, at least as it was given to me, said to round to the nearest tenth, I believe. Let me double check my numbers on the other side here. Yeah, round to the first decimal. So again, this doesn't mean that our sales were $2,617. It means that it was 2,617.4 million. Or as I would probably say, sales were 2,617.4 million. And that's the amount of sales we had. But if you're being asked to write it in millions, your answer is actually, and it kind of seems weird to say it this way, but the answer in millions is $2,617.4 million. That's our answer here. And then same kind of deal for S of 40. So the sales when time is equal to 40 years and 40 years after 1980, right? Time equals 0 is 1980, time equals 40, 20 years later, 40 years later in 2020, same deal, 150 times 1.1 to the 40th power. So all I'm doing is on my calculator, and I tried to find I was trying to find a TI calculator I could show you guys, but I couldn't find one online. So I'm just using my calculator, which you can't really, you can kind of see. Sure, so if you want to see what I'm doing here, I'm just doing this 1.1 to the 40th power, right? Looks just like that. You get something, press enter, you get 45-ish, and then I'm going to multiply it by 150. So times 150. And I'm getting this lovely number, 6,788.8. So I should write that as approximately 6,788 point, well, since it was 0.88, I should round it up to 0.9. And so my answer here is 6,788.9 million. That's the amount of sales we would estimate we would have in those years, right? It's not exact because this model was only for years between, like, I don't remember what I said. So something like between 1989 to 2004. So we're using this model to estimate the amount of sales we would have in the years 2010 and 2020. Okay. So the second part of this question, which wasn't asked, but I felt like was a good kind of extension of it, is to also estimate the rate of change of sales, which is just another way of saying, tell me what the derivative of this function is evaluated at the same time. Let's use the other side. So let's erase this. So again, our function S of t was 150 times 1.1 to the tth power. This actually, well, this means we're going to have to do something. And we're trying to find the rate of change of sales in 2010, which is just t equal to 30, and 2020, which is just t equal to 40. And the way you could at least express this way is you can say, well, here's what I'm really trying to find. I'm trying to find s prime of 30. The derivative of the function, the rate of change of sales, so how fast sales are increasing or changing as time is increasing at this particular moment. So after 30 years of being in business, or 30 years from time zero, how fast are the sales growing? So we're going to take a derivative here. So first, before we can do this, we're going to actually need just s prime of t. Now, this actually is a function that we might not know how to differentiate yet. Well, he definitely, I know Merckx talked about it, and I did upload a video of it on YouTube, but I don't think many people have watched it yet, which is fine. So how would I differentiate 1.1 to the t? Well, let's go over here for a minute. So how would I take the derivative of, I'm going to do a slightly different example. Let's say I want to take the derivative of 2 to the x, which is like 1.1 to the t. I'm just using a slightly nicer base and x for my variable. We know the derivative of e to the x. That's equal to e to the x. And here's the nice thing about exponential functions. Their derivatives act very much like the derivative of e to the x. The derivative of e to the x is e to the x. The derivative of 2 to the x is going to be something like 2 to the x. Now, there's a couple different ways of doing this. One way of doing this, which isn't bad, I might give myself more room here. We'll come back to this. So one way to find the derivative of 2 to the x is to write it as the derivative of e to the natural log of 2 to the x. That is a perfectly fine re-expression of that function. This is not the way I love to do it personally, but eventually we're going to kind of just do it a different way anyway. And then the reason we would do this is then this x can come down in front here. So you're going to get, this is the derivative of e to the x times the natural log of 2. Now, last class we talked about the derivative of e to the x being e to the x, and the derivative of e to the stuff using the chain rule is just e to the stuff times the derivative of that stuff. That's what we're going to do over here. We've got the derivative of e to not just x, but e to some stuff. So the derivative of this is going to be e to the stuff times the derivative of that stuff. And while this may look complicated, it's actually not complicated. This is x times a number. Right? Natural log of 2, it's like 0.7. It's just a constant. And when you take the derivative of, where's a different color pen here? Let's use red. When you take the derivative of, say, x times a constant, what's the derivative of 7x?
Seven.
Ah, thank you. Exactly. The derivative of 7x is 7. Or the derivative of x times 5 is 5. Or the derivative of x times natural log of 2 is just natural log of 2. So I get e to the x times natural log of 2 times natural log of 2. Now here's the thing about this. This looks not nice. And it really looks not nice if I'm looking at what I've written there. It's a little bit nicer. But here's the thing. This part here is really what we started with here, right? That is the same as that, which is the same as that, which is the same as that part here. So this part here is this part here. It's really just 2 to the x. So really my answer here is 2 to the x times natural log of 2. So here's what we actually end up seeing in general. The derivative of b to the x, where b is any of the usual bases, meaning b is positive and b is not equal to 1. The derivative of b to the x is b to the x times the natural log of b.
Is the 2 in the natural log being multiplied or an exponent?
Sorry, say that one more time. Is the 2 where?
In the natural log, like the ln, is that being multiplied or is that an exponent?
It's actually neither. So you mean like right there?
Yeah.
And so I maybe didn't write it very nicely, but it's the natural log of 2, right? You can't have the natural log without having something to take the natural log of. Kind of like if you have, it'd be like having a square root with nothing in it.
And you said that's the derivative of x times natural log 2, right?
Exactly right. And that's because the derivative of x times a constant is always just the constant. Good questions. Other questions about this? Okay, there is another way of finding this derivative, but I think we'll hold off on that for a minute, because it requires the derivative of the natural log of x, which we haven't talked about yet necessarily. So back to the problem we were actually doing. So the derivative of, so eventually you don't want to have to derive this every time. You really just kind of want to memorize that if you have b to the x, the derivative of b to the x is b to the x times natural log of b. So the derivative of 3 to the x is 3 to the x times natural log of 3. The derivative of 10 to the x is 10 to the x times the natural log of 10. The derivative of, it even works for e, of e to the x is e to the x times the natural log of e. But the natural log of e is equal to 1. So it's a useful formula that we use a lot for differentiation. All right. So here's what we were trying to answer. We were trying to figure out what the derivative of this function is. So if s of t is 150 times 1.1 to the t, then the derivative of this, well, if you have a constant times a function and you're taking the derivative, the constant just sticks around. In fact, that's really what I was doing over here. Right, the derivative of 7x, the 7 just hangs out and the derivative of x is just 1. So that's just going to stick around. And then the derivative of 1.1 to the t, well, just like the derivative of 3 to the x is 3 to the x times the natural log of my base. The derivative of 1.1 to the t, or x, I'm using t, is 1.1 to the t times the natural log of 1.1. Exponential functions, their derivatives always look a lot like the original function. Sometimes exactly like it if it's e to the x. All right, so, sorry, my hair is like on my forehead, it's kind of killing me. Now we're trying to answer the question, what's the rate of change of sales in this particular year? So I want to find s prime of 30. So I'm going to plug in 30 to this thing here. So I'm going to get, let's see, I'm going to do 1.1 to the 30th power. And then I'm going to multiply that by the natural log of 1.1 and 150. Where's my natural log button? It's right there. And then times 150 as well. So here's what I've got, just so you all can see it. I've got my 1.1 to the 30th power, which is about 17.5. And then I'm multiplying that by a natural log of 1.1 and 150. And I'm going to get 249.5 is what I'm going to round that to. So what does that answer actually mean? Oh, can I move the whiteboard? Do you want it closer or do you want it more centered?
Centers, please.
Sure thing. Let's see, I need to go that way. Sorry, 1 sec. Better?
Yeah, thank you.
No problem. Okay, so before when we were finding S of 30, it was the amount of sales in millions for that year. So S of 30, I think it's on the previous board still. S of 30 was like 2,600 million essentially sales. This is saying our sales are changing at this amount in millions per year. So what this actually means is that the rate of change of sales at year 30, so at year 30, sales are increasing because this number is positive at $249.5 million per year. That's the idea here, right? If S measures the amount of sales in millions, then the derivative measures the amount of sales in millions per some time unit. In this case, the time unit is years. And then we do the same thing for 40, right? We could find S prime of 40 is just going to be, it's going to be 150 million times 1.1 to the 40th power times the natural log of 1.1. Right, again, I'm just taking my derivative and plugging in t equal to 40. And calculating that, where's my calculator? I get 1.1 to the 40th power times, I want to get that out of the excellent though. Yeah, I like this calculator. It's a pretty good calculator. Times 150 times the natural log of 1.1. Where'd you go, natural log? There you are. And then it was 647.1. So that's going to equal 647.1. And again, that's in millions of dollars per year. All right. So, are there questions about this?
Yeah. Can you hear me? Okay.
Yeah, totally.
So we have to use that rule every time there's a variable in the exponent.
Sorry, can you say that one more time?
Function. So we have to use that rule for the derivative every time there's a variable in the exponent.
Well, generally, yes. So there's kind of two different versions, and actually, that's a great segue into kind of just talking about that in general. So, come on, board. Why you got to be so tight? I should just be smart and move it the way I need to that loosens it. Yeah, okay. Loosen it a little more. Let's go. All right, cool. Yeah, this side, I think someone like over tightened this and like pushed it in, so it just gets really tight over here. All right, so there's kind of two different things, and where do we need to start? Okay, so need that. All right. So for f of x equal to b to the x, where your base is a constant. Oh, sorry. Yeah, it was 600. Yeah, you're on top of it. 647. Yeah, I'm sorry, my 4 sometimes look like 9s. So for f of x equal to b to the x, like 2 to the x, 3 to the x, or 123 to the x. Anything where your base is a constant, then the derivative is just b to the x times the natural log of b. And you can certainly derive this formula every time, but it gets to be time consuming. Yeah, so well, there's somewhere else I'm going to go. So just so, and I suppose, sorry, there's a lot of different directions to go with this. But I suppose first what we're talking about is kind of the chain rule version of this. So, for example, if f of x equals 4 to the x, then the derivative is 4 to the x times the natural log of 4. What if my function is instead, I set the by, okay. What if my function instead is 4 to the x squared plus 3x? Well, the chain rule version of this is exactly like the chain rule version of e to the stuff, with one added thing. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of 4 to the x is 4 to the x times natural log of 4. The derivative of 4 to the stuff is going to be 4 to the stuff times the derivative of the stuff times the natural log of 4. Which would end up looking like 4 to the x squared plus 3x times 2x plus 3, right? The derivative of x squared plus 3x times the natural log of 4. So the only difference between 4 to the stuff, where your base is not e, and e to the stuff is this additional natural log of 4, right? If I was instead differentiating, right, if my function here was e to the x squared plus 3x, the derivative would be e to the stuff times the derivative of the stuff. And if you wanted to, you could also say to yourself at least times the natural log of e. The natural log of e is just 1. So we don't have to write that in there even though it could appear. I'm gonna go turn down the heat real quick because the heat is definitely on and my room is the hot room in the house. Oh. Yeah, it's kind of unfortunate. My wife has worked from home for the last year because that's what she does. And her office is in the office in our house, but it's the colder room and she likes it warmer. And my office is in the warmer room in the house and I like it colder, so oh well. Okay, so this is kind of the general idea. Let's what do I want to say here? Yeah. I want this to not be so damn tight. So here's how I would kind of summarize these derivatives of exponential functions. There's kind of like, there's probably like 4 to 8 things to say here. 4. The derivative of e to the x is e to the x. Great. The derivative of e to the stuff is e to the stuff times the derivative of stuff. Often your books or your teach, that's a wow, that equal sign is hard to see there. Often your book or your professor will write this either as the derivative of e to the f of x is equal to e to the f of x times f prime of x. Or sometimes they'll write it as the derivative of e to the u is equal to e to the u times the derivative of u. Again, it's just the chain rule, right? If you're replacing x with stuff, then your derivative, you always have to end up multiplying by the derivative of that stuff. We do it here too. It's just that our stuff is x and the derivative of x is 1. So we don't write times 1. I'm going to erase it because I don't like to write it. And then we have the other version of this rule where the base is something other than e. And everything is just going to change by multiplying by the natural log of that base. So the derivative of, I'll use b. B to the x is b to the x times natural log of b. And again, we're thinking of b as being greater than 0 and not equal to 1. If it helps you to think about it, think of b being like 2. The derivative of 2 to the x is 2 to the x times the natural log of 2. And then the chain rule version is the derivative of b to the stuff is equal to b to the stuff times, I like to write the derivative of the stuff first because I'm always thinking of the chain rule first, times the derivative of the stuff times the natural log of your base. All right. So I want everyone to try to do the following on their own. First, find the derivative of e to the x cubed plus tangent of x, and then find the derivative of 5 to the same thing, to the x cubed plus tangent of x. Go ahead and try that on your own while I go refill my water. I like the whiteboard. I don't like the dust from the pens, but oh well. Okay. I'm going to go ahead and flip the board, and then we'll work on the answers. That's super tight. So the derivative of e to the x cubed plus, I think it's a tangent, probably. Yeah. So that's going to be e to the stuff times the derivative of that, which is 3x squared, plus the derivative of tangent is secant squared x. Derivative of 5 to the stuff here. Does anyone want to share their answer? Anyone brave?
5, then the exponent x cubed plus secant, or x cubed squared.
X cubed.
Wait, the first part. X cubed plus tangent x. Times 3x squared plus secant squared x times natural log of 5.
Perfect. Good job. Thanks. What I want to emphasize that's important to make sure you guys get is that this derivative of the stuff here does need, I wrote it kind of small, does need to be in parentheses if there's more than one term. So if you have something plus something else or something minus something else, you need parentheses around that because it's supposed to be all of this multiplying that. and that. So just be a little careful there. Right, good job. That's exactly right. Okay, so yeah, we can do one more. Let's see, what do I want to do? What time is it? So why don't you guys try this one? Find the derivative of, let me show you, yeah. 7 to the x to the 4th minus 3x squared plus sine of x. Go ahead and find that derivative. Thanks for all the videos and the pictures. I like seeing you all, even though you look tiny to me. I can't really see you all that well, but it's good to see your faces. I don't need to see my face. Okay. I'm just going to go ahead and tell you guys what the answer is. So the nice thing about exponential derivatives, the function you're differentiating is always going to reappear exactly as it is. So the derivative of 7 to the stuff is 7 to the stuff. Times a couple things. The derivative of this stuff, which is 4x cubed minus 6x plus cosine of x times the natural log of the base. Natural log of 7. Okay. So let's go ahead and so there is another type of exponential function. Well, I wouldn't really call it an exponential function. There's another type of function where you have an x or a variable in the exponent, but you also have a variable in the base. And to be able to do those types of derivatives, we have to talk about the derivative of the natural log of x first. So I'm not sure if you've covered this in class yet. I feel like I saw it in Merckx's notes, but I didn't see it covered very clearly. Maybe I just didn't see it then. So the derivative of the natural log of x is 1 over x. But I'd like to talk more about that because that doesn't seem very descriptive to me. So there's 2 different ways you can find this derivative. One of them depends on knowing the derivative of e to the x already, which we did. We know that the derivative of e to the x equals e to the x. And more importantly, we know the derivative of e to the stuff is e to the stuff times the derivative of stuff. I know I'm saying that a lot, but it's really, really important. So let's pretend like I didn't know that this was the derivative of natural log of x. And I want to find the derivative of, and I'm going to use y equal to the natural log of x because I know I'm going to end up using implicit differentiation. And to do that, you kind of have to have an equation. So I want to find the derivative of the natural log of x, but I'm pretending like I don't know how. So what we're going to do is we're going to rewrite this. We're going to rewrite this y equal to the natural log of x as an exponential equation. So if y equals the natural log of x, I know it's hidden from us, but what's our base?
Is it e?
Yep, definitely. It's the natural base e. So this is e to the what power? Is it y or is it x? Actually, don't answer. here's what I want you guys to do. I want you to click on yes if you think it's X and no if you think it's Y. Because I want to try and get people to use the yes and no buttons because I kind of like them. So yes for X, no for Y.
Wait, what was your question?
Sure. So is this, am I writing this, is this going to be e to the y equals x, or is it e to the x equals y? So I want you to click on no for this and yes for this. And you guys remember how to find the yes and no? It's under the managed participants thing, I think, which is at the bottom. If you click on that, you can see stuff over here. Ah, yes, I see some of you. I see a couple yeses, I see a couple no's. Okay, so if I'm rewriting this, thank you guys. I think most of you responded, not quite everyone. That's all right. I do want you guys to try. All right, good. All right, cool. So it looks like people are going back and forth. Yes, no, yes, no. I don't know. So here's what it is. So, and in fact, here's what I really think of. If I can't remember how this works, I think of the equation log base 2 of 8 equals 3. 2 to the third power equals 8. Log base 2 of 8 equals 3 because I'm saying 2 to the what equals 8. Oh, 2 to the third equals 8. This is the equivalent to 2 to the third equals 8. So when I'm reading a logarithmic equation, I see that my base is here, my exponent's actually over here, and it's equal to whatever's inside the logarithm there. So if I'm seeing this as the log base e to the this power y equals x. I think there was something else I wanted to say. Oh yeah, there's another way you could totally do this, which I wasn't thinking about until just now. You can also just do this for both sides. You could say e to the y equals e to the natural log of x, and then e to the y equals x, because e to the natural log of x is just x. There's a couple ways to get there. And now we're going to differentiate both sides. And here's where we have to be extra careful. The derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. That's where we're using implicit differentiation. What's the derivative of x?
One.
Yeah. I know you guys know it. Again, I want to make sure everyone's cool with this. Right? When you differentiate e to the y, you e to the y times the derivative of y. Because again, y is a function of x, right? Y is equal to natural log of x. So it's really kind of like we're just doing the derivative, of e to the f of x and getting e to the f of x times f prime of x. I'm just using y instead of f of x. All right, but now I'm going to solve for y prime, because if y is equal to natural log of x, y prime is going to be the derivative of natural log of x. So y prime equals, divide both sides of e to the y, you get 1 over e to the y. And then replace e to the y with what it's equal to, which is x. So I get y prime equals 1 over x. So the derivative of the natural log of x is indeed 1 over x. Are there questions about that? Because it's a very important kind of concept to make sure you're very comfortable with. It's going to come up quite often.
Do you mind just re-explaining the part where you rewrote it? I just got a little lost.
So when I'm thinking about a logarithmic equation in general, like my favorite one is log base 2 of 8 equal to 3, because it's easy for me to remember. But you could also think of something like, I don't know, log base 3 of 81. Again, when I read a logarithmic equation like this, what I'm actually saying inside my head is 3 to what power equals 81? And I know that that's 4, because 3 times 3 is 9, times 3 is 27, times another 3 is 81. So log base 3 of 81 is 4. Or log base 3 of 9 is equal to 2, because 3 squared equals 9. So a logarithm always equals to the exponent. What exponent, you might ask? The exponent that you have to raise this base to get this result. So I know that each of these can be rewritten. This can be written as 2 to the third equals 8. The base to the power equals the stuff inside. This can be rewritten as 3 to the fourth equals 81 again. And I often think about doing this, going here, and then going there. You'll often see people write that. Here I'm thinking 3 to the second power equals 9. So what I did here was I said, oh, well, what I've really got, and I'm kind of running out of room to erase over here. One way of doing this is thinking, I've got y equal to, usually we don't write log base e, but I'm going to write log base e this time. Log base e of x, which is just the natural log of x. It's just a different way, a less typical way of writing it. And then this becomes, my base is e, it's raised to the y power, it's equal to x. That's what we're doing there. Another way of doing that, if you don't like doing it this way, is just saying, not really, I'm over here. Sure, it's just right over here. If you've got y equal to the natural log of x, you can also exponentiate both sides and say, okay, well, that's the same as e to the y equal to e to the natural log of x. But e to the natural log of x is just x, right? E to the something and the natural log of something are inverse functions. They undo each other. So e to the natural log of whatever is just the whatevers in the parentheses there. So two different ways to go about it. Other questions about this? Time is it? Oh yeah, we got plenty of time. Okay. So the reason, there's actually a number of reasons I want to talk about it, but the first thing I want to do with that is actually show you an alternative way to find the derivative of 2 to the x. So we found the derivative of 2 to the x. Well, in fact, we all know what the answer is. So take a minute. I don't need you all to tell me, but just think about what the answer is for the derivative of 2 to the x. Hopefully you're all thinking the same thing I'm thinking, which is that it's 2 to the x times the natural log of 2. And the way we got there last time was we did this thing where we said, oh yeah, the derivative of 2 to the x is the derivative of e to the natural log of 2 to the x. Right? We're actually using that idea that the e to the natural log of some stuff is just equal to the stuff. Right? The e and the natural log. I don't want to say they cancel, because that's not quite the right word. I would say they undo each other. So then we wrote this as the derivative of e to the x times natural log of 2, and we took the derivative using the chain rule, right? We got e to the stuff times the derivative of that stuff, which was just natural log of 2, and then we remembered that this was just that, right? 2 to the x is e to the natural log of 2 to the x is e to the x times natural log of 2. So this is just 2 to the x times natural log of 2. But now I'm going to show you a different way of doing this because it's actually, I think, a more useful way of doing it. So to find the derivative of, say, y equal to 2 to the x, we're actually going to use what's called logarithmic differentiation, which is going to necessitate the use of implicit differentiation. So first off, when you see a function that's got a variable, so I should back up a little bit. Normally, if you're going to differentiate this, you should just memorize the formula. Right? The formula for a constant base is straightforward. Derivative of 2 to the x is 2 to the x times natural log of 2. Works for any constant base. And we also know there's a chain rule version where you could have like 2 to the whatever, and the derivative of 2 to the whatever would be 2 to the whatever times the natural log of 2 times the derivative of whatever. Right? We've done a couple examples like that. But there's another thing that we're going to use this other method for, and it's kind of nice to start with this example first. So when you're trying to take the derivative of something that might be terrible with a variable in the exponent, and usually also the variable in the base, you take the natural log of both sides. And the whole reason for taking the natural log of both sides is so that you can bring down that variable outside of the exponent. And, get the variable out of the exponent in front of the log. So we can say that the natural log of y equals x times the natural log of 2. And now we're going to differentiate both sides. What's the derivative of the natural log of y? Anybody? Anybody?
Isn't it just 1 over y?
That is mostly correct.
Oh. Is it times also the derivative of y?
That is absolutely correct. Right, so just like the derivative of, and I guess we didn't really do examples like this yet. When you take the, did we? No, we did not. But it's the chain rule, right? The derivative of the natural log of some stuff. I guess we should talk about the chain rule version of natural log, but we'll get there in a minute. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. What's the derivative of x times the natural log of 2?
Is it 1 times 1 over 2?
Oh, you're so close. It's 1 times, so the derivative of x is 1. The natural log of 2 is just a constant. In fact, we kind of did one like this before. The derivative of x times a constant is just 1 times the constant.
Oh, okay.
So now, if we solve for y prime, we get y prime equal to y times natural log of 2. But y is 2 to the x. So we get y prime equal to 2 to the x times the natural log of 2, which is surprising to none of us because we already knew the derivative of 2 to the x was 2 to the x of natural log of 2. But this is another way to do it. And the reason we're talking about this example really is because we want to eventually be able to do something like the derivative of x to the x, or x to the sine of x, or tangent of x to the x, or other crazy things. I'll open my window here. It's getting kind of stuffy in my room. Hopefully it's not too bright. No, it's fine. Yeah. Is that fine? Yeah, it's a little bit much there. Let's do this. That should be okay. Yeah, we're not getting weird about it. Okay. So before we get to that, I think we should do a few chain rule versions with the derivative of log of x, natural log of x. So this is going to be a thing I say a lot because it's true. If you know how to take the derivative of a function of x, you know how to take the derivative of that function of some stuff. It's just the usual chain rule variation where if I know the derivative of the natural log of x is 1 over x, then I also know that the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. People often prefer to rewrite that as the derivative of the stuff on top of the stuff. That's fine. I like writing it that way too. It looks nicer. I just prefer to write it like this because this kind of really shows more the chain rule nature of what's happening. You say, oh, I'm doing the derivative of my outer function, leaving the inside alone, and then after that, multiplying by the derivative inside. And I think I'm missing all your chats because somehow I got scrolled up to the top here. There's not, no, I'm not missing anything. It's fine. Just want to make sure I'm not missing anything. If you're writing something and you see that I'm not seeing it, just speak up. So if I wanted to find, say, the derivative of the natural log of, I don't know, what's a good question here? X to the 19th power plus x squared. Well, that's going to be 1 over all that stuff times the derivative of all that stuff, which is 19x to the 8th plus 2x. And that should definitely be in parentheses. And depending on how the question was asked, I would probably just leave it like that. But if they said to simplify, I mean, I would probably write it as 19.
Wouldn't it be 19x to the 18th?
Yeah, it would. Thanks. Yeah, 19 minus 1 is not 8. So that's what that would look like. My 18 there is real. Let's make that look a little better. And you could probably even simplify that further. Like you probably factor out an x from the top and the bottom. You cancel it. I don't care. No one cares. I mean, not no one, but people don't really care. A couple other things about this. Sometimes some simplification can happen. So, for example, if I was trying to take the derivative of the natural log of, let's see here. Sure, let's do this. X to the 7th. You can totally do the chain rule and say it's 1 over x to the 7th times the derivative of x to the 7th, which is 7x to the 6th. And this one is really easy to simplify. It's 7x to the 6th over x to the 7th, and cancel an x to the 6th here, and 6 of those there, and just get 7 over x. However, there's another way we could have gotten there. We could have also said that the derivative of the natural log of x to the 7th, well, we could have used one of the log rules that says, oh, if you've got x to a power, or I should say, if you've got a power on all your stuff in the logarithm, that can come down in front and say, I've got the derivative of 7 times the natural log of x. And then derivative of a constant times a function is just the constant times the derivative of that function, which is 1 over x. So I end up getting 7 over x that way as well.
Unless it doesn't like explicitly ask us to simplify, we don't have to, right?
Correct. So what I want to point out about this is sometimes people like to ask really kind of questions that look pretty gnarly unless you do some simplification using logarithm rules first. And I remember which way this turns to make it tighter. I'm like, which way do I go? I go this way. Or to make it looser. I don't want to make it tighter. There we go. Okay. Almost as I want to be just the right amount of tightness so that it doesn't wobble or move when I'm trying to erase or write things, but that it swings easily when I'm trying to rotate the board. Yep, these are the problems we have. Okay, so what if I was trying to take the derivative of, let's not get too crazy yet. Let's say I was trying to take the derivative of x cubed times cosecant of x. Well, this isn't so awful. You could totally do, maybe a natural log is what I also want to have in there. Sorry. Derivative of the natural log of x cubed times cosecant of x. You could certainly do this what I think of as the long way, meaning you could say, well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which I'm going to write just like this for the moment. And then I'm going to actually differentiate it. Now, if I'm differentiating x cubed times cosecant, I'm going to have to use the product rule. So I'm going to get, let's go ahead and write this on top because it does look nicer if we do it that way. So my denominator is x cubed times cosecant, and my numerator is the derivative of x cubed times cosecant. So product rule, we take the derivative of one part and multiply by the other part left alone. And then we reverse it. We leave the first part alone, and we multiply by the derivative of the other part. And the derivative of cosecant x is negative cosecant x cotangent x. And you can totally leave it like this, although it's Not very simplified like this, but oh well. An alternative way of doing this. I'm gonna leave myself a little bit more room because you'll see it that way. So let's write it down here. The derivative of the natural log of x cubed times cosecant x. Instead of using the chain rule and the quotient rule, sorry, not quotient, I meant product, I can use my logarithm rules to break this up. I can write this as the derivative of the natural log of x cubed plus the natural log of cosecant x. Right, when you have the natural log of something times something else, you can break that up as the natural log of the first thing plus the natural log of the second thing. And then to make it even simpler before I differentiate, I could, love it. I could bring this 3 down in front and say I've got the derivative still, right? I'm just simplifying, so I still have to write that I'm taking the derivative. 3 times natural log of x plus the natural log of cosecant of x. That looks worse, sorry. And now that I've simplified this logarithmic expression as much as possible, I can write that it's equal to, so the derivative of 3 times natural log of x is 3 times 1 over x. And the derivative of the natural log of cosecant of x is 1 over cosecant of x times the derivative of cosecant of x, which is negative cosecant x cotangent x. And I would probably simplify this because it's easy to simplify. 3 times 1 over x, I would write as 3 over x. And 1 over cosecant times negative cosecant cotangent, cosecants can cancel. I'm just going to get minus cotangent of x. And that looks a heck of a lot nicer than this mess here. You could totally get from here to here. In fact, it's not that hard. If you break this up into 2 separate fractions, so this is 3x squared cosecant x over x cubed cosecant x plus minus of minus x cubed cosecant x cotangent x over x cubed cosecant x. Here you can see an x squared, and the x squared will cancel, and the cosecant cancel to give you the 3 over x. Here, x cubed cancel, cosecant cancel. You get the same answer, but in my opinion, it's way less challenging, at least to think of it, doing it the second way. And while this one isn't so bad to do either way, like doing it this way is fine, doing it this way I think is better, but still fine, there are worse problems. So let me give you an even more heinous example, and then we will finally circle back around to the question I want to answer, which is taking the derivative of something like x to the x or sine of x to the x, which again, there is an example of on the YouTube. I will also remind you all that if there are things you want to see me make short videos of, I'm happy to do that. You just have to let me know. Definitely people that have asked for certain things have gotten them, unless I've misunderstood. I feel like there was one person who asked me for a log thing. I wasn't exactly sure what they meant, so I tried to do my best guess. But if you have things you want to see short examples of, I'm more than happy to make that happen for you, as long as I don't miss my voice. So yeah, we got the time, okay. So I want to find the derivative of this heinous looking terrible thing. X to the 7th times the square root of x cubed plus 1 over, let's make it not too terrible, cosine of x times x, 3x plus 2 to the 9th power. Hopefully y'all can read that okay. I feel like I got kind of small at the bottom there. Remember that again. The cosine of x times 3x plus 2 to the 9th. Okay, so that's what I'm trying to take the derivative of. And before, so I do not want to do it the long way, meaning I do not want to think of this as 1 over all of this times the derivative of all of this, because the derivative of all of this, I'm going to have to use the quotient rule, the product rule twice, and probably the chain rule a couple times as well, right? It's a lot. the intent of a problem like this, if you ever see something that looks nasty like this, your teacher means for you to do the following thing: to use your rules of logarithms to break this up into many smaller, simpler functions. So I can break this up as the derivative of the natural log of the top. And it's better to write roots as powers. So instead of the square root of x cubed plus 1, I'm going to write that as x cubed plus 1 to the 1/2 minus the natural log of the bottom, cosine of x, times 3x plus 2 to the 9th. And then the natural log of these products, I'm going to break up one step further. Notice I'm writing the derivative each time. I'm also going to mention, when you're doing something like this, you should either be only simplifying or only differentiating this step. You shouldn't be doing some of both. So I don't want to differentiate until I've simplified fully. So then I'm going to break this up as the natural log of x to the 7th plus the natural log of x cubed plus 1 to the 1/2 minus the natural log of cosine x. Yeah, I'm talking about this. Plus the natural log of 3x plus 2 to the 9th. Now, the way I've written this, it's actually a little bit wrong because it's minus this entire logarithm here. So I'm actually going to throw some parentheses around this thing here, which is equal to that thing there. So this minus sign actually distributes across there. Here's the thing I remind myself every time I do a problem like this, right? I've got a natural log of some gross stuff. All the different pieces in the top have logarithms that are positive. Natural log of x to the 7th, natural log of 3x plus 1 to the 1/2. All the factors that are in the bottom, cosine x and 3x plus 2 to the 9th, are going to have negatives in front of their logarithms. I'm going to get a negative natural log of cosine of x, and I'm going to get a negative natural log of 3x plus 2 to the 9th power. That's always true. All the things in the top always have positives. All the things in the bottom always have negatives. All right, one more simplification, and then we'll differentiate. So to simplify further, you're going to bring all the powers down. So this is still equal to the derivative that I haven't taken yet of 7 natural log of x plus 1/2 natural log of x cubed plus 1 minus, there's no power to bring down here, natural log of cosine of x minus 9 times natural log of 3x plus 2. Okay, finally, we are ready to take the derivative. So since I'm actually going to take the derivative, I'm not going to write the derivative symbol anymore. So I'm going to get 7 times the derivative of the natural log of x is 1 over x plus 1/2, right? These constant multiples just hang out in front. Derivative of that is 1 over x cubed plus 1 times 3x squared. Again, you can write the 3x squared on top of the fraction. You probably want to. Minus the derivative of this is 1 over cosine x times negative sine x. If I was going one step further with simplification, I would definitely rewrite this part as plus tangent x, because sine over cosine is just tangent. And then finally, minus 9 times 1 over 3x plus 2 times the derivative of 3x plus 2, which is 3. And there's definitely some simplifying we could do here, but that's not really the point of this question, so I don't want to. Yeah, we definitely have enough time to get back to where I wanted to get to, which is good. All right, so I'm going to turn the board because we are running out of time. But if you want to come back and look at this later, you can obviously look at the video that will end up being on YouTube as soon as I can get it up there.
I just have a quick question.
Yeah.
On that problem. Did you put minus 9? Was it because that one was on the denominator?
Correct. Well,
Like
because right here, so I have minus the natural log of all this, and then the natural log of all this was the natural log of cosine plus the natural log of that.
Oh, okay.
Minus sign here distributes to each of those things.
Oh, okay.
But yeah, more generally, I just remember that all the things on the bottom end up with a minus sign in front of them because of how the rules work.
Okay. Thank you.
Yeah, question. All right. So I know Merckx at least did the example of finding the derivative of x to the x. So I'm not going to do that one exactly. but the process is always going to be the same. So here's what I'm going to say first. For functions where the base is a constant, you can just use the rule, right? The derivative of 2 to the x is 2 to the x times natural log of 2. The derivative of 3 to the x squared is 3 to the x squared times the natural log of 3 times 2x because of the chain rule, right? And I'm not writing it down, but right, it's 3 to the x squared times the derivative of x squared, which is 2x, and then also the natural log of 3. But when you have a variable in your base and your exponent, there isn't, well, it's actually not true. There is a rule for it. The rule is super complicated and not something you should memorize. Instead, you should use what we just did, but not just did, sorry. Let me just do an example instead of trying to talk too much. So let's say I want to find the derivative of, let's make it fun. Let's make it secant of x to the x power. And this pen is starting to go. I'm going to go through a lot of pens, I bet. So when you have a variable in your base, right, there's a variable right there, and your exponent, this is when you really need to use logarithmic differentiation. So the second where we found the derivative of 2 to the x using the log of both sides, that's what we're going to have to do here. Now, we don't have both sides, so we have to rewrite this. Oh, I want to say I've got y equal to secant of x to the x. And then my goal is to find y prime. So before I can find y prime, I'm going to take the natural log of both sides to get this variable out of my exponent. So the natural log of y equals the natural log of secant of x to the x power. And then that x gets to come down in front. So the natural log of y equals x times the natural log of secant of x. When we did this before, when it was just a 2 here instead of a secant of x, when we did the derivative of the right-hand side, the derivative of x times natural log of 2 was just 1 times natural log of 2. But here, since this part x and this part natural log of secant x both have a variable, we actually are going to have to use the product rule to have a product of one function times another function. So differentiating both sides, what's the derivative of the natural log of y? I want to hear as many people talk as want.
It is 1 over y times y prime.
Exactly. And that's going to come up so much, right? You're going to be doing the natural log of y so many times, it's going to be like, oh yeah, of course, it's 1 over y times y prime. You really want to get that solidified in your head. And then the right-hand side is going to be kind of gross. I'm going to have the derivative, so the product rule. So the derivative of x is 1. And then I leave the other piece alone, which is natural log of secant x. Plus, now I leave the x alone. And the derivative of the natural log of secant, well, the derivative of natural log of some stuff is 1 over the stuff times the derivative of the stuff. And the derivative of secant x is secant x tangent x. All right, there's 2 more steps, which I usually like to do as one step. So so I'm going to write the final step, and then I'll go back and fill in the intermediate step. So the final step, I'm going to multiply both sides by y. But I'm actually going to replace y with the fact that y is equal to secant x to the x. So my final answer is secant x to the x times all this stuff here, which is the natural log of secant of x plus x times, I can cancel a secant here, it's just x times tangent of x. The intermediate step that a lot of people like to write is when I multiply by y, I'm just going to bring over y and get y times all this stuff. Natural log of secant x plus x times tangent x. But I think it gets to be, like, I know what y is going to be. Y is going to be what I said y was equal to. So my derivative here is secant x to the x times the natural log of secant x plus x tangent x. And we're going to see always with these is, if you're taking the derivative of secant x to the x, you're always going to end up getting that same function back, because you're always going to get 1 over y times y prime, and then this y is always going to come over to the other side, and it's going to be the function you started off with. This part here is a little bit messier though, so we really do need to use this process to find these derivatives. All right. So are there questions about this? All right, hearing no questions. I know I didn't give you a lot of time, but we are pretty much out of time. So good seeing you all. And I will put this up on YouTube as soon as it finishes processing or loading or whatever it does when you close Zoom. And if you guys have questions, send me an email, start a discussion thread on Canvas. And if you have videos you want to see things of, just let me know and I will try to make some. All right, I'll see you all later.